Good afternoon, everybody. I said at the end of last lecture that I thought we would change the syllabus order just a little bit, and I've decided that we are going to do that. We may continue with the lecture that is scheduled for today, depending on how this goes, and I have put it up on the website. I just put it up a few minutes ago. But what I want to do is take a quick break and from our regular lecture material and talk about GDB for a little bit. And I want to do that for two reasons. One is that when I was looking at the schedule, I feel like we're going to be getting into the material for your Project 5 just a little bit earlier than I would like to, in part because I want you to still be focusing on your Project 4, and in part because I know that, 2 weeks from now you will forget everything that I said today. So I want to put that off by one more lecture. So my plan is to start that either end of this lecture or beginning of next lecture rather than starting it now, which will push it back basically by, the most of that material back by into next week. So that's one reason. And two is that I think it's time to grow a little bit in terms of your usage of GDB and debugging and things like that. I think there are things that you can learn that will be valuable for you in your PA4. And I also think that it's just something that these techniques will be useful to you potentially for a lifetime of programming. So I want to talk about GDB. And what I would like for you to do here is I have some content that I want to go through, but I also would like for you to drop your questions into the chat as you normally would. So this is going to be a cross between a normal lecture and an office hour, sort of, in that it's targeted and there's lecture topic and there's specific content I want to talk to about, but I do want you to stop and ask about the things that I'm doing, because I'm going to go through it and I anticipate that there will be questions about, I've had to do almost that before, right? How would I do this instead? That sort of thing. So please do ask if you have those questions. So what I'm going to do is I have queued up, I have the GDB lab here in my on my virtual machine, and I also have a fresh checkout of the malloc code on my virtual machine, and then I think we might actually write some other code, depending on where this goes. And what I want to do is sort of engender some circumstances where things that you might run into, and then show you how you would use GDB to tackle those things, to find out what you might want to know about how your program is running. And I am going to run GDB both just at the prompt and then also in Emacs using GDB mode, because I do think that there is real value in using a front end to GDB rather than using GDB directly. And there are a variety of those front ends available, GUI front ends, as well as just scripting packages that run in your GDB. And I'm not going to show you necessarily those scripting packages or the other GUI front ends or show how to set those up, but there's a lot of options out there. And what they have in common is every time your debugger stops, they show you more than just where did it stop, right? They show you a little bit of extra context that you're likely to want to know, which saves you time in figuring out what's going on with your programs, whether that's local variables or a backtrace or whatever. Vasu, we can talk about your seg fault, but this is really not open office hours in that sense. This is open office hours in the sense that we are going to talk about how to use GDB specifically. Alex, same answer. I really want this to be focused on GDB. But one of the things we are going to talk about, for example, is if your project is seg faulting, how do you find out where? Because for this project, that can be a little bit harder than for some other projects. So what I want to do here first is I'm going to dive into the GDB lab that we did as a source for a program that we know has bugs and will crash, etc., and then look at sort of some of the things that we might do with GDB in that lab. So I have that here in this directory, and as you can see here, I guess I don't have a colored ls here, but this debug file is an executable. You can see that from this x over here, right? These x's in the permissions is the executable, and then public.c is the source code that you have for that executable. And the first thing I want to show you, because this comes up in your malloc, is when you run a program and it crashes, how do you find out where it crashed and what sort of circumstance it was in when it crashed? So it's not that you ran your program in GDB, you just ran your program and then it crashed. And printf will cause seg faults with malloc. You should not use printf for debugging in your malloc in particular. Always use fprintf to standard error, as I've said for multiple projects throughout this semester. Fprintf to standard error, one of the things that it guarantees is that it will not allocate memory. Printf might allocate memory. And yes, Sarah, I'm absolutely going to go over what to do if you segfault a command that you run. So, okay, so let's look at that right now. Let's look at what happens if I run a command and then it segfaults, and I want to know what happened. The standard error by default goes to your terminal. So this program will segfault if I run it, right? This is the GDB lab. If you remember, it segfaults. So I run it and it segfaults. And notice that it says here, segmentation fault core dumped. What that means is that when the program was done running, when it crashed, it wrote a memory image out of what the program was doing when it crashed. But if I look here, I'm probably not going to find one. Yeah, I'm not going to find one. There is not a core file here. And the reason is that the machine defaults to not saving that information. And it defaults to not saving that information because these core files can be very large and you don't necessarily want them all over your disk taking up space if you're not a programmer, right? But we are programmers, and so we want this information. And there is a shell command called ulimit that lets you set whether or not you want to save core files. So if I run ulimit, let me run ulimit-a, it will tell me about all of the things that can be limited or unlimited in my shell. Ulimit stands for user limit. And one of the things that we see here is at the top here, it says core file size in blocks. Blocks are disk blocks. They're a 0.5 kilobyte. Is set to 0, which means that if a program tries to dump core, it should deny the program from dumping core. But I can run the command ulimit-c unlimited. So we see that it said -c there. So now if I do ulimit-a, we see that it says core file size in blocks is unlimited. So now that the core file size is unlimited, in this terminal, not everywhere, but in this terminal, if I run a program and it crashes, it will leave a core file. So if I run this debug, so if I look in this directory, I have nothing but the debug file and public.c. But if I now run this debug program and it crashes and I list the directory again, I now have a file here named core. And I think we talked about this 2 lectures ago or 3 lectures ago, what core is. And core was a memory technology that used to be used, and we use the word core to mean the main memory of a program still. So what happened was this program ran, it crashed, and the operating system took the main memory of that program, all the memory that it was using, and it wrote it to this file in a special format that GDB understands. So now if I want to know where this program crashed, I could run GDB as I normally would, /debug as I normally would, and then give it a third argument, which is that core file, the name of that core file. And I could rename that core file, right, if I wanted to save it or something like that. So I do gdb /debug core, and I run it. And this is just how GDB would run at your prompt, right? I'm essentially just running it at the prompt here. And I can see in this GDB that it crashed on public.c line 72. So I can open up public.c, go to line 72. Oops. Go to line 72 and see where it crashed, right? And it's the same line that's listed over here. Now, a couple of other things that you've seen before but maybe didn't pay a lot of attention to that are helpful to you is when I'm at this GDB prompt, if I type list, it will give me, by default, I think 5 or 7 lines of code. It's more than that. 10 lines of code, I guess. Where the middle-ish line is the line that I'm currently crashed at. So on this screen right here where it crashed, this is a stack frame. We'll look at stack frames here in just a second. And it says that we crashed on public.c line 72, and it prints what public.c line 72 is. But when I type list, it prints a few lines before line 72. Then it prints line 72, and then it prints a few lines after line 72. So I can get an idea for where I am at the time that it crashes. But at any rate, it crashed here where it tried to write number sub I equals I plus 1. But that doesn't necessarily tell us why it crashed. But the magic of the core file is that not only did it keep track of what the program was doing and where it was when it crashed, but it also kept all the variables and all these things. So I can say print I, and it will tell me the value that I held at the time that this program crashed. And it says, okay, I equals 708. Well, let's go ahead and look at my backtrace here. So I type backtrace, and this backtrace is a representation of the stack frames on the computer. If you remember, we talked about the stack and how stack frames are created. This is the stack, right? So it says that the stack frame 0 here, which is the stack frame I'm currently in, that I'm currently executing in, is in the function initialize array, and these are the sort of values that it has right here. And it's at public.c line 72. It's where it's executing at the time that it crashed. But that was called from. So the previous frame on the stack, if you remember our sort of stack layout, our stack grows downward in memory. And so this is saying that we have a stack frame that is main on the stack, and it has the program counter and whatever. And then we have a stack frame that is initialize array, and it has the local variables I and the arguments, they would be up here, the numbers array, etc., right? Exactly as we talked about when we talked about the automatic memory management, and this stack would grow downwards, right? So this is our number 0, and this is our number 1 when we run that backtrace command. So I was in main at public.c line 50. So I can go over here to public.c line 50 and see that I'm calling initialize array with the variable numbers as an argument. And I can ask it where, that didn't do what I wanted, where numbers came from. It didn't work in my, my Emacs is insufficiently set up apparently to just tell me where it came from. But it's right here. And that numbers array has 5 entries. Well, if I look over here in my GDB, when I printed I was equal to 708. So, like, clearly this is the problem, right? Is that I've run way too high. So let's go to our line 72 again. And how high are we counting? We're counting to len. All right, we're counting to len here. And if I look over here, the len argument is visible in my stack backtrace, and it's way larger than 5. So obviously we've counted past the end of our array. All right, so this is all basically stuff that you saw in the first GDB lab, but we are now doing it now, as we say, post-mortem on a program that has crashed, right, by using the core file. The big difference here between debugging a running program and debugging a program that has crashed on the core file is that I cannot ask GDB to do anything that would require a running program. So, for example, I cannot tell it to step and go to the next line, right? That's the next command, right? In. Because there is not actually a program being run. I can print I, but I can't print... Can I do that? Yeah, I can print I plus 1. I can't print initialize array of numbers and the actual length of the array, which is 5, because there's no program running. So I can't call a function inside the program as I could if I were running inside GDB. So this is very powerful in that it allows us to do things like use our allocator and just run commands and run them until something crashes. And when it crashes, analyze that crashed program after the fact, right? But on the other hand, we've given up a little bit of power in that we are not able to just manipulate the program as it's running as we would if we ran it in GDB and ran run. Now, what I can do is I can run this program from the beginning, wait for it to crash, and then do something that would allow the program to actually run. It looks like it's still crashed. I think because I'm still in the SIGSEG-V handler, so I can't run it from this particular place. But at any rate, I can now. It tried, right? It tried to run the code, whereas last time it just told me, "Hey, you don't have a process. You can't run the code." So that's the first thing I wanted to talk about is debugging a program that has crashed. And so the things that you need to know to be able to do that is you need to know the ulimit command. And you need to know that you want to ask it to make your core size unlimited. You don't have to make it unlimited. In particular, in this class, unlimited is fine. But in particular, if you were debugging something where in certain cases it might run away and just allocate bajillabytes of memory and you didn't have disk space to store that, then you could give an actual limit in disk blocks, right? You don't have to give it unlimited. You can give it a number of disk blocks. Unlimited is the most convenient because normally your programs don't allocate a bajillabyte of memory and you can just save the core file. How does the core file store the image of the memory of the process before it crashed? Magic. It uses black magic and chickens. The operating system has to help with this. So basically the operating system, it's actually not technically before it crashed. It is technically in the... It may be before it crashed. I would have to look and see how it's handled on Linux. I think it's technically in the segfault handler is where it does it. But the operating system basically halts the process, saves its image out to disk, and then kills the process. So it requires cooperation from the operating system. The program itself doesn't do this without help from the operating system because it would have to change its own memory in order to do this, right? So it gets help from the operating system. All right, so the first thing I want you to know is this ulimit-c unlimited. And Sarah, I think this is part of the answer to your question. So if you wanted to run ls with your malloc, right? So I have an allocator here. So I have an allocator here. And I can make this library, and this is just the checked out code, right? The original code. So I can do ld preload equals /libcsse malloc now, and then ls, and it's going to. It didn't crash. It didn't crash because it caught the null from realloc. So let me see if I can come up with something that will crash. Let me just run the shell. No, so I'll have to put in a stub realloc here to make it crash. But if it crashed at this point, it would leave a core file, and then if I GDB'd on that core file, it would load it with my allocator. So those of you who have tried to run in your allocator in GDB, you know that it's tricky to get it to actually do that, and we'll see some other ways to do that here in a minute that may actually work. So question in the chat. Would it be possible to put a dead core dump image from disk back into memory and have it continue running, assuming the original bug was fixed within the dead image? The answer to that question is yes, but no. It's possible to do that. There are ways to revive a core file. They're not. I don't know that GDB can do it itself. It's beyond the scope of this class. It's harder to do in the scope of this class. It requires some extra work that we're not prepared to do right now. But it can be done. In particular, it is done with some frequency on embedded systems. Usually it does appear in the current directory, but usually it is suppressed. And you're right that this is something we had previously discussed. You need to run the command ulimit-c unlimited, which will cause it to not be suppressed, which will cause it to actually write the core file. On some platforms, core files are not written to the current directory. And on some Linux distributions, core files are not written to the current directory. It will be written to some other directory someplace, usually in /temp or /var someplace. But that's dependent on your distribution, on your operating system, etc. I can't answer where that would be. The LD preload line does not necessarily create a core file, but it will run the program. And if core dumps are enabled and the program crashes, then it will create a core file. So let's cause that to happen, right? So let me open mm.c, and I will make ls crash by doing this. Right, so this is not a valid implementation of realloc. This doesn't work, but it should cause something to crash. Oh, it worked. Wow. Wow. Why you do this to me? Why is it working? All right, now we're going to get a crash. Okay, segmentation fault, core dumped. So now if I do an ls, you'll see there's a core in this directory. So now I can gdb ls, because the program I ran was ls, and core, and do a backtrace. And in this case, it crashed in ls someplace. And the reason is that it wasn't actually my heap allocator that crashed. I caused ls to crash internally by doing a realloc that did not actually follow the rules of realloc. So in this case, this backtrace is not very useful to me. But if it had crashed in my allocator under different circumstances, then now I could look at that backtrace and I could examine my allocator. It didn't because of the way I engendered that crash. Are there additional programs that would be good for torture testing malloc and realloc? Really, ls and ps, the reason that they're in the testing list is because ls and ps are unreasonably hard on the allocator for what they do. In particular, ls uses realloc as both malloc, realloc, and free with different arguments. And so all of those functionalities have to work, and it uses realloc aggressively, actually reallocating memory, which is why this crashed right here. It did not, I didn't do the copy that realloc has to do. And so it crashed. Okay. So another thing that I want to show you here, before we maybe write some code and then debug it, is how I would run attempt to. Now, this will not always work, but sometimes it will work, and it's worth trying. How I would attempt to run a program using my allocator inside GDB. This does not always work. We'll see if I can get it to work right now. Sometimes it does work. When it does work, you have all of the advantages of running the program using your allocator inside the debugger. But unfortunately, because of the tools that we're using, it sometimes confuses GDB or just flat out doesn't work. So in order to do this, I'm actually going to go into GDB mode. And I am going to debug bin ls. And it says it has no debugging symbols, which is expected. Now, I'm in GDB mode in Emacs now, which we've looked at before, but I want to go through it again quickly. So my top left here, where my cursor is where I would type my GDB commands. The buffer immediately to the right of that shows me my local variables and the contents of my CPU registers. I can go over here and click on registers, and it will show me the contents of my CPU registers. Now, I'm not running the program right now, so there are no CPU registers to examine. And furthermore, in this class, probably you don't care much about the CPU registers. There are times that you would care more about that, but we're not learning assembly code, etc. This buffer over here on the middle left is a list of the currently open buffers right now. And ordinarily, this would be a listing of the source code of the program. But because I don't have source code for LS, it showed me a buffer list for some reason. Probably so I could open the source code if I wanted to. But if I were debugging a test that I wrote, my source code would be over there. On the right here, in the center of the screen, is the actual output of the LS program. On the bottom left are the stack frames, if I were to break it at some point in its execution. And on the bottom right are the lists of the breakpoints that I have set. So if I run the program here, what we will see is all of this will return to approximately where it is right now. But in the output, we will see the actual output of the LS program run. Now, in this case, it looks like it ls/bin. It apparently ran the program in /bin, which is where I loaded it from. And so this buffer over here contains the output of the bin directory on the computer. Now, this is one of the nice things about running GDB in a GUI or a wrapper of some kind, a driver of some kind, is that you can separate these concerns. So on my GDB prompt over here, it basically just says run, and then it has the GDB debugging information about running, and then my GDB prompt back, and all of this LS output didn't get spit out into that same window, right? It was separated to a different location. Furthermore, if I had had breakpoints and stuff and I had manipulated those would show up as well. No symbols means that this program was not compiled with debugging information, and so GDB doesn't know how to show me anything about the debugging of the program. Like if I do break main might work actually. Yeah, so break main, no, it didn't work, right? There's no debugging information for main. Will it work when I run it? It did not. It wasn't able to break because I don't have symbols. So that's what that means. But what I can do, and this is what I wanted to show you, is so I'm going to delete breakpoint 1. I'm going to run it. I'm going to try. I don't know if this is going to work. I'm going to try to run it against my allocator, as you would to debug against your allocator. And in order to do that, I'm going to use the setenv function. I thought it was setenv. Yeah, it's set space env. Okay. So the setenv function lets me set an environment variable inside GDB that will affect the programs I run, but will not affect GDB itself. So one of the problems with using your allocator and running inside GDB is if you do ld preload equals whatever GDB, then GDB is using your allocator, and so your GDB is probably going to crash, right? So I am going to set env ld preload dot slash, actually I'm going to give the whole path. Which should be this. And then I'm going to run it again. And so this time it crashed, and I got actually the crash from it using my malloc. Now, how do you get these windows? I ran mxgdb. So you press Alt and then X so that you get this little mx prompt that I have down here. And then you type GDB and hit enter, is how I got all these windows. And so if we look here, we can see that we do in fact have all kinds of information given to us about the running of this process right now. but it's not as useful as it might have been. Because we don't have debugging information. So, for example, my list of stack frames down here, they're all just question marks, right? But that's fine. All right. I'm going to kill this ls, and I'm going to run it again. And this time what I'm going to do is say, okay, why don't you break in malloc? And it will say... Oops, I think I hit page up. Yeah, it'll say that it can't find it. But I think... Hang on. I broke stuff. Okay, yes. Okay, it loaded malloc. If I run it, though, it should break in my malloc. Did it? It didn't. See, this is what I was saying. You can confuse GDB, so it didn't work this time. Sometimes it will. I think maybe if I ran on something that I had in this local directory, it would work. But it will certainly work with tests that you write. You know, your mileage may vary in what kind of useful information you can get out of this running with LD preload in GDB. But I did want to show you that it can be done. I'm going to quit GDB mode. I did want to show you that it can be done. But as I said, there are tons of caveats, and I'm not going to spend time to figure out what just happened there, because there are tons of caveats, right? It doesn't always work. What does always work is doing this. Oh, no wonder it didn't. It's not using my ls. Why is it not using my ls? Oh, this worked, actually. It was only when I listed a larger directory that it didn't work. Right? Yeah, okay. Right, makes sense. That will work, and then I can always debug that core file. That will always work. The only thing is that if you're running a system binary, it won't have debug symbols. So if it didn't crash inside your allocator, then, you know, your debugging may be of limited utility. So in general for PA4, debugging the core when you crash is a great technique. A better technique is writing tests, linking them against your malloc, and running those tests in GDB. But that requires writing tests. And for whatever reason, I cannot get any of you to write tests. You just won't do it. I give you assignments to write tests. I tell you to write tests. I put entire paragraphs in handouts and readmes on how to write tests. And I say, what tests have you written? And you say, I haven't written any tests. So that's the best way to do it. But recognizing that you won't do it, looking at those core dumps is a reasonable way to do it. So I want to pause there quickly and say, like, I know that was a lot of information, but are there any questions? Like, for example, Sarah's question was, how would I run GDB against one of these programs? And I just showed you a couple of ways to do that. Are there any questions of things you have wanted to be able to do in GDB and you have been unable to do? If so, what are they? And can I now show you how to do them? While you think about that and types of questions, we will write a quick little list library and then maybe a program to link against it. Can we GDB our tests to verify them somehow? Yes, if you write tests, you can run GDB against your test. So the difference is, if you look in the makefile for your malloc, if you look, the tests are actually linked directly against your source/mm.o, so they don't have to use that LD preload, which means that you can just run GDB and then your test, and it will always use your allocator, and you will be able to debug it directly in that fashion. Is there a way to start GDB in a for loop after a certain number of iterations? The answer to that is it depends. We saw in the GDB lab how you can do that if your for loop is iterating over an index, because you can just set a watch point for the index to be equal to or not equal to or whatever, whatever it is that would cause you to need to break your loop. If you're doing something like iterating over a list where you don't have that easy index to run a watch point on, it becomes more complicated. If you can't come up with a watch point, then the answer is no, you can't do that. But keep in mind that watch points can examine like the values that are stored in a list node. So Sarah, the GDB ls core not telling you the line that it crashed, that's because ls doesn't have debug info. That means that it's crashing in ls, not in your code. So as mine was, my code wasn't crashing, but my code was also not correct, and it was causing ls to crash sometime later. And in that case, the crash is in ls. ls doesn't have debugging symbols, and so therefore I don't get the information about where it crashes. How would I read and use the information given to me by Valgrind? I found this to be an issue 2 PAs ago with PA2. Yeah, so Valgrind is another great test, or another great tool for you here. So let me see if I can... actually, let me do this on malloc. You can't use Valgrind with malloc. So that may be the short answer to your question, is you can't use Valgrind with malloc, because one of the ways that Valgrind works is by replacing malloc with its own allocator that it can use to do memory debugging. And so if what you're debugging is malloc, it'll replace your malloc with its malloc, and then it effectively uses an LD preload. So you can't use it from malloc. But if you were using on something else, let's see if I can get Valgrind to give me a... Oh, that's right. There's no test for PA3 IM. All right, so we'll go to my list that I was working on here, and we'll get something that we can run Valgrind on, although we're going to run out of time here. We'll give it -ggdb-o0 because we're debugging. That makes life easier. Standard is C99. Wall W error. Okay. I'm not going to do anything for my all just yet. Make O files from C files with... All right, okay. So then I'm going to define a quick list API. All right. And then we'll start with just a single function, which is a prepend. Actually, let me just do this to make it more obvious. All right. And I see questions in chat, but let me go ahead and do this. Okay, questions in the chat. Is it possible to use GDB test name core? Yes, absolutely. Absolutely. I'm not sure if this has been mentioned. Is there a way to verify that our tests are proper by testing them against the default malloc? Yes. If you just don't link them against mm.o and you run them, they will run against the default malloc. So if you just copy the compiling line that make test would do and don't link them against the default malloc, then they will do the right thing. All right, so now we have a list prepend function. So let me write a test file. So all right, it's taking more time than I wanted. All right, so now that should run the test. Okay, why doesn't it compile? Of course it doesn't. Why? Oh. Duh. Okay. So now I have a program that I can run against, right? It's called test prepend. If I run test prepend, it just runs, right? It just works. So now I can run valgrind against this. So here's the output of valgrind that someone had asked about. And right here, so this is an important thing. So in use at exit, there were 16 bytes of memory that had been allocated in one blocks, which means it was a single malloc, right? It wasn't, if it said 16 bytes in 2 blocks, that means there were 2 mallocs and they added up to 16 bytes. Then down here, leak summary definitely lost 16 bytes in 1 blocks, which means that there was, I allocated memory of 16 bytes, and there is no pointer to this anywhere, and so it's lost forever. And it says I can rerun with leak check equals full to get that information, and I think this is probably the other kind of output from valgrind that you had questions about. This is an error for a specific error. And in this case, it's saying that the memory that was lost was created using calloc, and that calloc was called by list prepend. So this is a backtrace, basically. These lines right here are a backtrace, a set of stack frames. So we have main called list prepend, called calloc, and that is the memory that was lost. So what this tells me is if I wanted to get rid of this test, I should probably look at test prepend.c line 9. Sorry, line 9. So right here, I am allocating a list node, and I'm never freeing it. So then if I just free list... Oops, don't do that to me. So now, if I run it, it should tell me, yeah, nothing was lost. So those are the kinds of output that valgrind will give. Now, the error that will come above it Here it says that it was a loss record. Sometimes it will say access 1 byte past memory allocated or something like that. That means you overran the end of an allocation or an array or something like that, right? There are different errors that it can give, but each one of those will be followed by effectively a backtrace, right? A GDB style backtrace. So again, though, that's of limited use for malloc. All right, so let me engender another kind of crash here, and then show again, what we would see or what we would analyze in malloc. So let me do this. We're going to write an append function. And what we're going to do is we're going to run all the way off the end of the list. We're going to let our loop run too far. Actually, and that's it. I'm just iterating the list. And then I say, actually, I'm going to use good programming practices, and I'm going to use prepend to create my new node. Because it'll do exactly what I want if I just prepend a null. Right, so if prepend is right, then now my allocation and initialization is right. And then I'm going to say this, and then return curve. So this is a bug, right? Because if either the list is empty, or if the list is had elements, I walk past the end of the list, then try to insert the elements. So I'm actually inserting at the wrong place, right? So I'm going to crash. So then let's do a test append. And I may run just a couple minutes late here. If you have to go, go. But I think this is valuable material. You can always catch up on it later. So then I'm going to write a test append. Nope, I want standard lib. Let me start out with a this, and then I'm going to append to this list. All right, so I should have a list of element 1, element 2 if everything works, right? So now I need to modify my makefile. Why did you do this to me? Oh, because I didn't, I don't have this in. Oh, this is why I don't live code. Typos. And also, this is not my normal Emacs configuration, so I keep hitting the wrong key bindings. Okay, so now if I run test append, it should crash. Yep, it crashes. All right, now we'll see a GDB in an environment where we can actually use a lot of those extra windows, right? So I run Alt-X GDB. And I don't want to run bin ls. I want to run test append. And if I run now, then when it crashes, note that some of these frames have useful information to us that they did not have before, right? So in particular, on the top left, it actually tells me the line that it crashed at, and it has usable information. On the bottom left, it actually has the call stack. And these call stack in Emacs, in the Emacs GDB mode, these call stack items are clickable. So if I click test.append C, line 9, it actually took me to test.append C, line 9, for some reason here in this upper left corner window, which is not where I would expect that to be. And then, in addition, it set the local variables here in the top right to be the variables that are in main, not the variables that are in the frame that crashed, etc., right? If I wanted to, I can go to registers, and I can see what all of the registers on the CPU are. Again, we don't necessarily need that in this class. And it also set me to the right frame in GDB, or did it? It didn't, actually. Yeah, it did. It did. Okay, so it set me to the right frame in GDB. So if I'm moving up and down my stack in GDB as I normally would, then you can see my my local variables here in the top right. Right now I'm inside the list append function. If I go up, now I'm in main, and the locals are for main. And note that my source view on the left-hand side in the center top to bottom switched to the main function. It's also very hard to see because this font is super tiny for some reason that is unclear to me. But there's a tiny little angle bracket right here. That is the line that I actually crashed on. So when you run your own program, this will actually give you useful output. And this is why I say write your own tests. Don't necessarily just use the tests that are given to you or that are just the system programs or whatever. But that does mean that you have to write tests that are useful and usable and tell you the things you want to know. Now, Lysander put out a video yesterday that has it's a great video. It's only like 5 minutes long, so please watch it. That gives some advice for like how to determine what you should test, right, and what should be in your tests, and writing stress tests and things like that. All right, we've run over time. I told you I was going to do that, but I don't want to keep you too long. So I will say, if there are any quick questions that anybody has that I should grab before we go, please throw them at me. Otherwise, I hope I've given you a few more tools to put in your bag of tricks for debugging to help you be able to debug your malloc effectively. So ulimit-c unlimited, which will cause core files to be dropped. GDB, the name of a program, the name of a core file, which will allow you to post-mortem debug a program. And then sort of a little bit more about why we might use a graphical GDB program to debug a program, and what the difference is between debugging something that has symbols, debugging symbols, and something that doesn't. Where is the video posted? There is a link to it on Piazza. And there is also, it's also findable through UB Learns if you go to Classroom Videos under, I think, Review and Miscellaneous or something like that. There's another category other than Lectures that has the video. Good question. Will there be a lecture quiz? Yes, there will be a lecture quiz. What will be on the lecture quiz? I don't know. I do agree and understand that it was a bit fast. The lecture quiz will probably cover the things out of this that I want you to remember, so you might go back and find them. For example, you can expect that one of the lecture quiz questions, the answer will be ulimit-c unlimited, right? Where can we find the commands that I have been using? So the GDB lab covers almost all of the GDB commands that I've talked about today. We've maybe applied them in slightly different ways, but the GDB lab covers all of them. The ulimit command, the only reason I would expect you to know that is that we just talked about it right now, and that's one of the reasons that we I mean, it's been mentioned on Piazza and some other times before, but that's one that you would just need to know. I don't know that we discussed any other specific commands. I think this was mostly not teaching you... Oh, set env and gdb, we did talk about. I think this was mostly not teaching you new things that you'd never seen before. It was more teaching you that some of the things you've seen before can do things you didn't know they could do, or how to use them to achieve the things that you didn't know how to do. So I'm not sure if that answered your question or not. Okay. I don't see any more questions just rolling in. So thanks for your attention. I know this was non-traditional. This isn't how we normally do lecture. This is the sort of thing that I might actually have done just a pre-recorded video for. But I did want to, I don't necessarily want to give you a bunch of extra content. And I wanted to push back a day. So I thought we'd just use lecture time for it. So thanks for your attention. I hope that's helpful to you. On Friday, we will actually pick up with the processes, threads, and concurrency lecture that was listed for today. So thanks a lot, and I will see you on Friday.